All right, here's our problem of the today. What is the coefficient of friction between a book and a table if it takes you 5 newtons to push the 10-kilogram book? Now this is going to require some assumptions. First of all, I'm going to assume that I'm just able to get that book started at that 5 newtons. So I'm overcoming that static friction, that occurs between two surfaces when they're not moving. It's that maximum coefficient of friction. So I'm going to consider the situation when the acceleration is 0. And I know you may be thinking, well, Miss First, we're actually talking about when we're just starting to accelerate it. Well, that's exactly right. Because we're just starting to accelerate it, if I solve this problem, if I consider it for when acceleration equals 0, that's going to be the threshold between no movement and just getting started. I'm going to do this problem the same exact way. If you look at any of my other force summation problems, you'll see they're not that difficult if you strategically, or if you just use the strategic system of doing force summations. You don't even really need to think. You just have to be very systematic and always start with your free body diagram. So just to draw a sketch, I always like to draw a sketch just so that I'm sure I understand what's going on. Another assumption that I'm making with this problem is that this push force is horizontal. The only reason I'm assuming that is because they didn't state an angle at all, so I'm just going to assume that it's horizontal. And we're giving it a push of 5 newtons. Again, I'm going to consider that threshold moment between no movement and just getting started. So we actually can make the assumption that our acceleration, well, it's not really an assumption as much as it is, this will be that threshold point. And the book itself is 10 kilograms. So I'm just going to do it the same way that I always do. I'm going to start out with my free body diagram. Okay, now I know I'm on Earth. Oh, I guess that's another assumption. So I have my force of gravity always acting downwards, as we discussed before. Now I imagine I'm the book. Be the book. Be the book. What do I feel? Well, I feel the table underneath me pressing upward. And I also feel this irritating person pushing on me from my left-hand side. Now, it is convention. We use the convention here to always have your vectors pointing away from your free body diagram. So because we do that, if I say this is my applied force, saying this or taking that vector and moving it over to this side is the same exact thing. Remember, vectors, as long as we keep the same length, which represents the magnitude, and angle, we can really move them anywhere we want to when we're dealing with rigid bodies, and they stay the same. Their values stay the same. Now, also, if I'm a book, underneath me, I feel a pulling. I feel, here's the book, I feel like a pulling, and that pulling is going to be that coefficient of friction. So here's the question. Which direction is the friction acting in? Friction always opposes motion or intended motion. So if we're trying to get this book just moving to the right, our coefficient of friction is going to be to the left. I'm being very serious when I say the physics is pretty much done at this point. Yay. No, not yay. But yeah, the physics is pretty much done. Now we just blindly do a free body diagram. Okay, I'm going to do my force summation in the x direction. All of my horizontal, let me not forget my axes. I'm going to use a standard axis where my x value is going to the right. That to the right is positive. X to up is going to be positive y. So when I sum my x forces, I have my applied force and my friction force. Well, I notice here that friction is acting to the left, so that friction is going to have to be negative. I'm also going to do a force summation in my y direction because this is a two-dimensional problem. So in my y direction, I take a look at all of the vertical forces, all of the forces going up and down. I have my positive normal force, and I'm going to add that to my negative force of gravity. And again, gravity is negative because it's going in the opposite direction as my positive y-axis. So now I'm just going to simplify. It's simple algebra at this point. What I mean when I simplify is I'm just going to replace what I know and move downward. Well, there are two relationships that you should know, and if you don't, today's your day to learn them. The first relationship you should know, love, understand is that the force of friction is equal to that coefficient of friction. Here we're going to be talking about the static coefficient of friction because the book and the table are not moving relative to one another, and we're trying to overcome that static coefficient of friction times the normal force. The other relationship that you should always know is that F sub g, your gravitational force, is equal to the mass times g. And do not forget, g is not negative 9.8. G is the magnitude of the acceleration due to gravity, and it's 9.8 meters per second squared. So these are the things you should have in the back of your head. And of course, Newton's second law, which is force equals mass times acceleration. Well, if I'm going to add up all of the forces in the x direction, Newton told me that's equivalent to the mass times the acceleration in the x direction. So I'm just substituting. The applied force, I know what that is. That's 5 newtons. And my friction, I don't really know what that is, but I know what it's equal to. It's equal to that coefficient of friction times the normal force. And I can also plug in the mass here, okay? So my mass for this object is 10 kilograms. 10 kilograms. If you have the propensity to getting confused, I would highly suggest that when you do make a change, you just make it one at a time and always substitute one thing at a time and move downward. Now at this point, what am I going to do? I have two unknowns. Do I panic? Well, that's an option that a lot of students take and choose, but no. Deep breaths. Remember, the most important thing is to relax and move to the other side. Here I have May. Newton's second law tells me that the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, normal force, and then I substitute in what I know. What I know to be the gravitational force is mass times g. And again, a lot of these things are going to come automatically to you. I'm going to plug all of this wonderful information in. My mass is 10. G is 9.8. Now here, because I'm assuming the acceleration in the x direction is 0, again, that's not so much an assumption as it is I am going to, it's not an assumption, I am going to use that as my threshold point between no movement and just getting started. So we cancel out on the left-hand side here. And now we simply play a little algebra. All right, so you see, when I got to this point, I had two unknowns, but instead of panicking, I just said, you know what, I'm not going to panic. I'm just going to go to the other side and simplify my y equation as much as possible. When you do these force summations, your answers are going to fall out. We really truly didn't even have to remember we were looking for the coefficient of friction. We just do our force summations and see what falls out. So on the right hand side, what fell out was that normal force was equal to 98 newtons. Ooh, well, let me look back and see where I was stuck. I was stuck here, and now I can plug that 98 newtons in here, further simplify, and I end up with -5, and I'm going to take out my very high-tech calculator. It's extremely advanced, and I'm going to find out that mu is equal to 0.0510, I take a look back at the problem and I see here that I have one significant digit, and so I'm going to round my answer to one significant digit, and the coefficient of friction to just get that book started, 0.05. There you have it. Way to go. Make it a great day.